Okay, we're gonna start chapter 8. We're gonna talk about the concept of friction. Friction is a pretty important concept because we have every system in real life has friction somewhere. So you have friction between surfaces. Um, you design systems to have high friction, like transmissions, where you don't want to have um, the components slip. You want it to stay in place. So you design components to have high friction, and sometimes you design components to have low friction. Kind of like in this case, if you minimize the friction, your energy is maximized. You can go further. But in brakes, you want to maximize friction. So we have to definitely talk about the concept of friction because it's very important. And once you move through your studies and you learn about thermodynamics, you'll see that friction also um, has to do, also contributes to something called heat. So if something has a lot of friction, usually gets pretty hot, and you have to design systems to cool down, like the pistons in an engine, you have the oil. But heat usually translates to losses, so energy losses. So your system gets less efficient by um, gaining heat, and the more friction you have, the less efficient your system is. But again, sometimes you want to have high friction because that's really the goal of the system to be able to avoid slip. So regardless of what your design is, you have to consider friction either to minimize or maximize. So, for example, a system that has friction in many components, like any system in engineering has friction somewhere. And if you take the engine, for instance, there's friction between the pistons and the jacket. And of course, you inject oil to avoid or to minimize the friction. Obviously, you have friction between the wheel and the road. In racing, that is pretty important. You want to minimize the friction, but still you want to be able to capture a good grip when you're in a turn, but minimize the friction when you're on a flat or a straight line. Transmission has friction, so you can change your gear. So really anything that you look at has friction. The brakes obviously has friction. You want to minimize your friction so that the airbags can deploy. Um, the springs, the suspension has friction. Everything that you look at has friction. And depending on what material is in contact with other material, your friction could be pretty high or pretty low. All right, so we're gonna talk, of course, about the concept of frictionless. That's the ideal case where there's no energy loss. Then we're gonna introduce friction forces and different types of surfaces. And there's also types of different types of friction, as we talked about, for lubrication and for mechanisms that require low friction. Okay, so right here we have the concept of this could be a tire, or this could be a train, or this could be just a box. This is just a system. It has a weight, so there's a force and the vertical axis, negative force. And of course, there's a force, a reaction force on the ground, keeping the force from going down. This is just Newton's law of statics, of the dynamics, really. When two forces are equal, there's no movement up or down. If you try to push this force forward, there's going to be a force keeping you from moving that forward. That is given by a friction coefficient. And different materials have different friction coefficients. So the concept is very straightforward. Up until the point where P is equal to F, there's no movement. Velocity equals 0. The moment where P is greater than F, the velocity is different than zero and you have movement. Okay? Then you can move things around. And F is given by the friction coefficient times your pushing force. Okay? Um, well, let me get rid of this so we can see the concept here better. There you go. So um, actually, I need to let me go ahead and restate that. Friction, the force of friction, is given by the friction coefficient times the normal force, not the pushing force, but times the normal force. So when P equals F, then there's no movement. Velocity equals zero. But when P is greater than F, then velocity is different than zero. And then to clarify, F is given by the friction coefficient times the normal force. And the normal force is the same as the weight, but in a positive magnitude. Okay? So really what this means is that when P is greater than the friction coefficient times the normal force, then you have movement. So if you were to compare the points right here, P is the amount of force, so this way P is going greater, and this going up, the force, the friction force is going greater. So up is greater, to the right, the pushing force is greater. So there's a point where P is equal to F at any point up until you get to move the box. And that maximum, then you have the same friction force, even though if you have more pushing force. So you need to overcome that friction force first so that you have movement. Now, there's also the difference between kinetic and static friction. So up until this point, your friction is static. Later, you have your kinetic. So it's greater. Your static friction is greater than your kinetic friction because it's tougher to go from rest to moving than from moving to moving faster. All right, so here we have some values that are already in a table for you, experimentally or from design. Yeah, from design of experiments, engineers and scientists found these coefficients, and these are approximate values for static friction, and this is for dry surfaces. So if you have a metal on a metal, kind of like on a train, uh, or really the wheel of the train is metal to metal. You have the wheel and then you have the railroad. This is going to be 0.5 to 0.60. This is really depending on many factors, the type of alloy, the type of steel, the temperature. Temperature also has a huge factor. If it's warmer, you have less friction. If it's cold, you have a lot of friction. That's why it's always good to let a engine warm up a little. The same thing with if you've seen Formula One, they let the tires warm up before they go racing. So how this reads is that your force of friction is this value right here, ranges from 0.15 to 0.60. So what this means is that it goes from 15% to 60%. So the force of friction is up to 60% of your normal force. Remember, the normal force is the force opposite to your force of because of your weight, your Fw. So if something is pretty heavy, your friction could be up to 60% of that force. So you have to apply a force, a pushing force, that is up to 60%, well, that's why they put it in mathematical terms, of 0.6 of your normal force. Metal on wood, depending also on the type of metal, the type of wood could be from 20% to 60%. Metal on stone could be up to 70%, meaning that 70% of the weight of your system has to be, there's a force that has to be 70% of the weight in able to be able to push it. Metal on leather is from 30 to 60%. Wood on wood could be from 25 to 50%. So of course, depending on your application, you want to be on the minimum side or the maximum side. If you want to be able to move things, you want to be on the minimum side. If you want to be able to keep things static, you want to be on the opposite side. Wood on leather, 25 to 50%. Stone on stone is almost 70%. Earth on earth is almost 100% of the force. Rubber on concrete is 60 to 90%. So it's not very efficient, but the thing is that rubber is very very durable. So even though it's not very efficient, you can use it for a long time. So that's why we use rubber for our car, for our wheels and tires. All right, so the kinetic friction is approximately 75% of the static friction. So your static friction being these guys right here, your kinetic friction is 75% of that. So it's going to be a little smaller. And this is, as a rule of thumb, is really independent of the area. This is just, in general, we keep this as a general concept. If you want to go into details and make your system more efficient, then you have to do experiments and dial in this number. But as a rule of thumb, it's just 0.75, your static friction. That's why the static friction is on the table. And then from those values, you get 75% of that for your kinetic friction. So as I said, if there's no friction, so really the normal force is P times W, right? It's like air. When you push things up and down, you have almost no friction. Gravity is affecting, but not the air. However, as I said, that I remembered that when you have an airplane, definitely has drag, which is a concept related to friction. So what we mean by no friction is that there's no force in the summation of forces in x. If this is your x, this is your y. There's no summation of forces in x in the negative axis. It's just basically it's a static equilibrium, not needing to have any forces on the left or on the right. But if you do have friction and you have a small p right here, if that p is smaller than the static friction times the normal, then you're still in equilibrium. So no friction is the ideal case. All right, and as we said, if you have a pushing force that is in an angle, then you go back to the vector concept and you find the coefficients. And then in your x is going to be your cosine of theta times your p, and for your y component is going to be your p times your sine of theta. And p is the pushing force. And as we said before, for motion to happen, your pushing force has to be greater than your friction force. All right, so no friction, there's no motion. So if you have a pushing force that has an angle, your reacting force also has an angle, because obviously you have x and y components, and this force also has a counterforce. So sometimes they're going to ask about this angle right here. And a lot of times things are designed based on that angle. Okay, so if you want to find that angle, you can just use your sine, your trigonometry, the tangent or sine or cosine of your um, forces. But notice that your friction force, this is, as we said, is a static friction times your normal, and your vertical component is your normal. And this angle is opposite to your tangent. So in this case, your angle is simply tangent inverse of your static friction. So this is something you should remember. All right. So as I said, that angle right here, sometimes if you have that angle being the same as the tangent inverse of your static friction, up until that point, you have velocity equals 0. If your angle is greater, then you can have movement just because of gravity. So now we're going to start taking into account gravity as well. It's just these different concepts of how to set up your system, your coordinate system. The same thing if you want to stop the box with a force, then this has x and y components, and this has x and y components, and this has x and y components, and everything. You have to set up your system of equation, or you can just set your system of equation like this, x and y, and the only one that has components with respect to x and y is this guy. So you decide which one you want to do. You're gonna get the same results. So the friction force is always opposite to the sense of motion. This is pretty intuitive, but we do have to mention that. And applied forces, of course, will, once you start moving, an applied force against the movement is going to be subtracting the the movement, the force of the push. So the push could be also to contain or to stop. So let's look at this example, for instance. We have 300 pounds. This is the mass. So this is going to have a force right here. And they're telling us that this is the 3, 4, 5 triangle. So this is already telling us that this decided to take x horizontal and y vertical. That means that this guy has an x and a y component, and it has a normal force right here. All right, so if they're pushing this up, there's going to be a friction force down. All right, so let's see if they give us any information. Yeah, so a 100-pound force is pushing a 300 block or box up. Use your static friction as 0.25 and the kinetic friction as 0.2. So the same thing, actually here they decided to go a little simpler, and they put the x and y coordinates aligned with the box. And that's smart because then you have that force in x, and pushing force in x, friction force in x, then normal force in y, and then it's only your weight that you have to care about for your component in y, and a component in x for your weight. So if you set up the equations, you should be able to get everything that you need. So summation of forces in x, we have 100 pounds positive minus the component of the weight in x, so it's 300 pounds times cosine, so in this case it's 3 over 5, This is the same thing as cosine of theta. So since we don't have the theta, we just do um, the x divided by hypotenuse. So it's 100 minus the x component of the weight minus the friction is equal to 0. So we have one equation, one unknown. We found out that the friction force is actually 80 pounds. All right, summation of forces in y is normal plus, or minus in this case, minus the y component of the weight. So it's 4 over 5 times 300. If you solve for normal force, it's going to be 240 pounds. So the force normal to this box is 240 pounds. All right, so that's pretty simple. So the sign is just basically to give you this sense or the direction of the force. Now calculate the maximum friction force. And all right, so in that case, we said that the maximum friction force is they gave us static friction, and we know what the normal force was. So 0.25 times 240 equals 60 pounds. All right, so actually this force was greater because this angle was greater than the angle given by the static friction force. So you need only 60 pounds positive to just because we're finding the magnitude. But really this could have been negative 60, depending on the sign of your friction force. Okay, so since the friction force is smaller, then the plane will slide down. This is a typical question in this type of problem. You find your friction times your normal force, and if it's less than your normal component, then you decide if it's less, it will slide down. If it's bigger, then it won't. It's pretty simple.